copy of the previous Lesson 4 project and renaming it to Lesson 5. If you are just joining the course, you can download the previous projects from statemachine.com/quickstart. Get inside the new Lesson 5 directory and double-click on the workspace file to open the IAR toolset. If you don't have the IAR toolset, go back to Lesson 0. So this is the program you created in Lesson 4. It works in that it manages to blink the red LED on the Stellaris Launchpad board, but it is certainly not very readable, because it is full of cryptic numbers and there are no comments to explain what's going on. To improve the readability of the code, it would be very nice to use names for the registers instead of the cryptic numbers. One way you can achieve it is by means of the C preprocessor, which lets you define any piece of code as a macro. For example, let's define a macro for the first register you write to. Start a new line with the £, followed by the word define, followed by the name of the macro. The datasheet calls the register run mode clock gating control register for GPIO, so let's name the macro RCGC GPIO. After the name, you simply paste the piece of code this macro is going to replace. Once the macro is defined, you can use it instead of the original piece of code. Press F7 to check if the compiler accepts the code so far. The C preprocessor is called that way because it is conceptually a separate first step of simple text substitution before the real compilation. The preprocessor removes all lines starting with a £, so that the compiler does not see them at all. For example, you can define the macro to be anything, but as long as it is not used in the code, it doesn't matter and the code still compiles. Also, the preprocessor replaces only the macros that are actually used in the code, so the compiler sees only the replacement sequences of characters and never the macro names themselves. This means that the macro does not need to be any complete element of the C language. For example, the macro foo is just a piece of the pointer cast expression, but as long as the text substituted for the macro makes sense in the specific context, the compiler will happily accept it, because really the compiler cannot tell the difference. The corollary of all this is that you need to be careful how you define your macros, so that their meaning will not change unexpectedly depending on the context in which they are substituted. For example, to avoid surprises, it is always a good idea to enclose the macro like RCGC GPIO in parentheses, so that it always means dereferencing of a pointer in any context it might be used. It is also possible to define macros using other macros. For example, if you define the macro GPIO_f_base as it is specified in the datasheet, you can use it in the definitions of the other macros, such as GPIO_f_dir for the pin direction register, with the offset hex 400 from the base address. GPIO_f_den for digital enable with the offset hex 51c from the base address. And GPIO_f_data with the offset hex 3fc from the base address. Finally, it is always highly recommended to add comments to your code. Comments are only for the benefit of humans who read your code and are completely ignored by the compiler. The C99 standard supports two types of comments: the traditional C comment delimited by /* and terminated by */, such as this one, and C++ style comments starting with // and terminated by the end of line, such as these ones. Comments are allowed everywhere where you could legally place a space, and in fact all comments are replaced with a single space before the compilation. Both types of comments can also be used in the macro definitions. So now it will be interesting to see if this code still blinks the LED. To actually see this, I'm going to use the Stellaris Launchpad board. But if you don't have the board, configure the debugger for simulator and follow along. Great, the LED blinks as before, so all your changes seem to work. Let's examine in some detail how the compiler translated the GPIO_data macro and whether or not it introduced any overheads. After all, you might be concerned that now the CPU needs to add the base address to the offset at runtime. But when you step through the code, you can immediately see that the ldr.n instruction loads directly the full address hex 400253FC into R0 without performing any additions. In other words, the code is as efficient as before, because the compiler folds any constants computable at compile time and avoids unnecessary computations at runtime. Finally, it is very interesting to see which single instruction actually turns the LED on. It turns out that this is the str instruction. In other words, from the CPU point of view, talking to the outside world is fundamentally very simple and boils down to writing a specific value into a specific address. Okay, so your program still works and is as efficient as before. But I don't want to leave you with the impression that you have to define macros for all the registers yourself. In fact, typically you don't need to, because the microcontroller vendors, such as Texas Instruments in the case of the Stellaris board, already provide the macros for you in a separate file, which I have copied to the Lesson 5 directory. You can add this file to the project by right-clicking on the project and choosing Add Files menu option. The file name is lm4f120h5qr.h, which corresponds exactly to the microcontroller type on your Stellaris Launchpad board. The file extension .h means that this is a header file specifically designed for inclusion into .c files, such as your main.c. When you open the header file, you can see that it contains a whole bunch of macros very similar to what you have defined yourself. However, the pointer casts used in the header file are significantly different, which requires some explanation. Let me grab one macro from the header file and copy it to the main.c file for comparison. The first discrepancy is the pointer type. The macros in main.c use unsigned int, while the header file uses unsigned long. I will discuss data types in a separate lesson, but for now let me only say that on a 32-bit machine, like the ARM processor, the int type is 32-bit wide, so is the long type. So unsigned int and unsigned long are equivalent. So the real difference is the volatile qualifier. It informs the compiler that the object pointed to by the pointer might change spontaneously. When you declare an object to be volatile, you are telling the compiler that the object might change even though no statements in the program appear to change it. For example, 2 bits in the GPIO_F register on the Launchpad board are connected to the user switches. These bits can be changed when the user presses or releases the switches, which is obviously not caused by any program instruction. Therefore, the GPIO_F register, and in fact most other I/O registers, are volatile. This is important because the compiler can optimize access to non-volatile objects by reading an object's value into a CPU register, working with that register for a while, and eventually writing the value in the register back to the object. The compiler is not permitted to do this sort of optimization with volatile objects. Every time the source program says to read from or write to a volatile object, the compiler has to do so. So clearly, the volatile qualifier is useful for the I/O registers such as GPIO_F. But it can also be very useful for normal variables to prevent optimizations that the compiler otherwise might do. For example, the counter variable is used only in the 2 delay loops. But if you look at these loops from the compiler's perspective, they make no contribution whatsoever to the computation. Because the final value of the counter is either overwritten or discarded. In this case, the compiler is permitted to optimize both delay loops away. You can actually see this quite easily by allowing a higher level of optimization as follows. Click on the Project Options, choose C++ Compiler section and click on the Optimizations tab. Select High Optimization Level and click OK. Recompile and run the program on the Launchpad board. As you can see, the LED lights up and stays on all the time. When you single step through the code, you can see that the instructions for turning the LED on and off are still there, but the delay loops between them are gone. But now that you know about the volatile keyword, you know how to prevent the compiler from optimizing the delay loops away. You need to make the counter variable volatile. By the way, the volatile keyword can be placed either before the type, like in the macro from the header file, or after the type. I recommend placing it after the type. Let's quickly test whether the volatile counter indeed fixed the problem. Yes, the LED blinks. You can also see the delay loop when you single step through the code. So now, let's make use of the .h header file by actually including it into the main program. Again, you use the preprocessor for this. To include a file, you start a new line with a £, followed by the word include, followed by the name of the file in double quotes. Let's put the header file side by side with the main program to replace all the macros you've defined so far with the macros from the header file. The header file provided by the microcontroller vendor uses the register names from the datasheet, so you should have no trouble to recognize the interesting registers, such as GPIO port F data, GPIO port F dir, and GPIO port F den. If you have any doubts about the correct name of the register, you can always check its address to make sure that this is what you want. After replacing all the macros, you can remove your own definitions and recompile the code. Let's test the code one last time to check if the LED will still blink. This concludes this lesson about the C preprocessor and the volatile keyword. From now on, you are able to write programs that will run correctly at any level of optimization. So congratulations! In the next lesson, you will learn how to use the bitwise OR and AND operators to blink other colors of the composite LED, and you will also learn about the more advanced features of the GPIO register. If you like this channel, please subscribe to stay tuned. You can also visit statemachine.com/quickstart for the class notes and the project file downloads.